If you're like us, you're probably tired of showing people an incomplete CAD model. This tutorial will teach you how to animate chains in a way that makes them look great on your model, and it's easy on your computer. But before we get started, there are a few tricks we use when modeling chains that are important to be aware of. Instead of full links, we use half links. We do this because of the shorter dimension between repeating elements. Another trick we use is that the links don't travel all the way around like it appears in this animation. Instead, two straight segments and two curved segments only travel a certain angle, then reset themselves to their initial positions. This is accomplished through functions that we will get into later. The last trick we use is that we constrain the outer chains to an invisible pair of sprockets, as seen here, that are different from those in the final animation. This is done because the visible sprockets continue to rotate, but we want the chains to just move forward and back one link rotation. Let's get started. So here we have a folder, and in it there is a half link and a sprocket with 24 teeth, and they're properly modeled such that the links fit perfectly between the teeth. So now we're going to go ahead and make a new project. So new, and it's a single user, and we'll name it Chain Tutorial. And we want to make sure that we're putting it in the right place also. And save that. So now we're going to make a support to mount the sprockets and chains. Change the units to English, and it's a standard part, and create that. And the first thing we're going to do is make a 2D sketch. And you can select any one of these planes, it doesn't really matter. Click on Rectangle with a 2-point center. And then you can click on the origin and it will center your part for you, dimensioning it 1 inch by 1 inch. And then you can finish your part and extrude it. And we'll say 7 inches. And so that's the base of the bar. So now you can change the material of your part, and you want to be in Autodesk Material Library. And we'll make this part stainless steel. So now we're going to make axles that protrude out of the bar to hold our sprockets. So back into 2D Sketch, and you can make a circle right on the center there. 8 millimeters is usually the size of the axle that we use. And another circle on the other side. Then dimensioning them appropriately 1 inch away from the outside of the bar. And 5.125 inches from each other. And then it's always good to make sure that the distances from the top of the bar to the center of the circle are appropriate. And finish your sketch. And now we can extrude those circles. .5 inches. And that is the bar. So now you can click on Save As and save it as bar.
Exit out of this bar part and make a new assembly, and it's going to be in English standard inches, and place your bar. And now place your sprockets. Now you can use an insert constraint and constrain them to the axles. Now constrain the rotation of the sprocket with an angle constraint to the bar. And we always include the axis in the angle constraint to make the angles less ambiguous. And if you mess up on clicking the axis, you can click on 3 again and try again on clicking the axis. And then get the plane and the end of the bar. And apply. Hide the sprockets that will be visible in the final animation in order to work on the hidden sprockets. And save as. We saved it as chain tutorial, but you can save it as anything that you want. In our final animation, we have 2 sets of sprockets. In order to make the hidden sprockets, we have to open up our visible sprockets. So now we can save the visible sprocket as the hidden one. So sprocket 24 teeth hidden. Now to help you tell the difference between the 2 sprockets, you can change the color of the hidden one to gold. And you can save this. And now you're going to make a new assembly. And it's going to be in standard English inches. And place your hidden sprocket. And place your half link. And now with an insert constraint, you want to get the inside of the smaller pin of the half link to the sprocket. Make sure that you constrain it to a valley that has an axis on a work plane. Then constrain the other pin to the next valley with a mate constraint. And make a pattern. Circular. Then select your half link as the repeating part and your axis in the hole of the sprocket. And you want 12 half links in the pattern because that goes halfway around the sprocket. And the distance between repeating components in a pattern, otherwise known as pitch, is going to be 360 degrees of a circle divided by the 24 teeth in our sprocket. And then save as sprocket 24 teeth hidden 12 count. Exit out of this and place your hidden sprocket with the half links into your main assembly. And constrain them to your axle with an insert constraint. And now constrain the rotation of the sprocket to the bar with an angle constraint. And we're going to grab the axis of the sprocket first, and then get the plane and the end of the bar, and apply. And we're going to do the same thing with the other sprocket, but we're going to grab the top of the bar instead. And save it. Now that we're done with our curved chain segments, we're going to make our straight chain segments. So make a new assembly, and it's going to be in English Standard Inches. And place your half link. And make a pattern, rectangular, and pick your part. Now pick the direction of the pattern. So pick the edge of the half link. And you want 20 half links in the pattern. And go to Save As. And you want it to be chain number 25, half link, 20 count. Exit out of this assembly and place your half link 20 count into the main assembly. And you want 2 of these. Now constrain the curved chain segment with the straight chain segment with the insert constraint. So get the big end of the straight chain segment and the smaller end of the curved chain segment. The straight chain segment can still be freely rotated, so you need an angle constraint. Select 3 and select the axis that is connecting the straight chain segment with the curved chain segment. Now select the straight chain segment work plane, and for the final step, select the top of the bar. Now the straight chain segment should be parallel with the bar. And if you zoom into the other side, you can see why we place the axles 5 1/8 inches apart. This should be the worst case scenario. There are 2 ways to fix this problem. One way is to move the axles closer together, but in many models this is not possible. So the way we are going to show you is to split the difference between the 2 sides, so we would have a shorter chain segment on top and a longer chain segment on the bottom. Then rotate the curved chain segment to meet the new endpoints of the straight chain segments. Edit the offset of the angle constraint for the hidden sprocket and change it to 360 degrees of the circle divided by 48. 48 is double the number of sprocket teeth, which will rotate the sprocket half a tooth. Now you can see that the curved chain segment and the straight chain segment line up perfectly. Now let's make the bottom chain segment by opening up the top chain segment and editing the pattern. So you want to save this as chain number 25, half link, 21 count. And edit the pattern. Change the quantity from 20 to 21 links. Exit out and save. And now place the bottom chain segment that you just made and constrain the straight chain segment to the curved chain segment with an insert constraint. And grab the smaller end of the straight chain segment and the larger end of the curved chain segment. And the bottom chain segment can still rotate freely, so you need an angle constraint. So select 3 and select the axis connecting the curved chain segment with the straight chain segment, and select the straight chain segment workplane. And now grab the bottom of the bar. By adding the extra link, you can see how it lines up with the curved chain segment. Now that the chains are constrained properly, we can work on the constraints on our visible sprockets. So open up our sprocket 24 teeth 12 link. Hiding the sprocket in this file will turn off all of the hidden sprockets in the main file because the representation is associative. So once you hide the sprocket, you can exit out of this assembly. And you want to turn on your visible sprockets. The visible sprocket should be aligned with the hidden sprocket so it meshes with the chain properly. So let's give it the same angle constraint. Select 3 and select your axis. And select your work plane and the top of the bar. And the offset should be 7.5 because that's 360 divided by 48, which is what the offset was in the original angle constraint. Suppress the angle constraint you just made and constrain the two sprockets together with a motion constraint. Select the holes in the center of your sprocket. And this may be difficult to do with the bar visible, so you can hide that. And now select your holes in the center of the sprocket. And apply.
Now that our chain model is complete, the next task is to create the motion relationships between the components. We will be doing this primarily by editing and creating parameters. All of the component's motion is going to be cued off of the first sprocket's motion. That motion will be created by eventually animating its angle constraint. The value of the angle is something that is stored in parameters. The first thing we will want to do is edit its name so that it is more recognizable. So, select the sprocket and notice the angle constraint. This angle constraint is what drives the movement of the chains. Double-click on it, and you're going to want to take note of its dimension name. In this case, it's D2. Then, you can close that up and go into Manage Parameters. In Parameters, you can find that angle constraint and edit it. I'm going to give it a more identifiable name. How about Drive Angle to reflect its function? Okay, so now we are ready to put into effect a series of functions that will direct the chains we've made and placed appropriately to move appropriately. We are going to now make a user parameter by clicking on Add Numeric. We will name this parameter Drive Angle UL. And the purpose of this parameter is to convert drive angle's unit type to unitless from degrees. This needs to be done because we need unitless parameters in order to perform math. You'll get errors if you try to work with parameters that are in degrees. So the equation for drive angle UL is isolate, parentheses, drive angle, semicolon, degrees, semicolon, UL, close parentheses. The next parameter you will want to make is one whose value equals the number of teeth on the sprocket you are using. So we'll name this parameter sprocket teeth. And don't forget you need to be working with unitless parameters. You can either type UL or click on unitless up here. Sprocket teeth's value is 24 UL because the sprockets we are using have 24 teeth. We're going to add another parameter we named pitch angle. Pitch angle is the angle around the circle which goes from one tooth to the next tooth. The equation is created by taking the number of degrees in a circle, 360, and dividing it by the number of sprocket teeth. We created sprocket teeth so that we can put it in other equations, and if we ever have to change its value, let's say if we change sprocket size, then we would only have to change its value in sprocket teeth. Now you want to make a parameter that will direct the chains to seemingly move with the sprockets. We will name it chain angle UL. For chain angle UL to work properly, we need to do some math on drive angle UL, typing in drive angle UL modulus pitch angle. Modulus, represented by the percent sign, generates the remainder of dividing by the second number. In this case, modulus will give us the remainder of dividing drive angle UL by pitch angle. To give a little more perspective to this function, look at the equation for pitch angle. 36 divided by 24 equals 15. Therefore, when drive angle equals 15, the remainder will be 0. At any other number, there is a greater value for the remainder, causing the chains to inch forward from values 1 to 14 until at 15 they reset themselves to their initial position. Before this can be demonstrated, chain angle UL needs to be converted to degrees, since the constraint in the browser bar that controls the driving sprocket has to move in degrees. To make this conversion, I will add a new parameter named chain angle, and units should now be in degrees. The isolate command will be used again here. In the parentheses, write in chain angle UL semicolon UL semicolon degrees. The first unit is what it was. The second unit is what you are changing it to. So what has happened thus far is that drive angle has been converted to chain angle. This drives the hidden sprocket based on the calculations being done to the visible sprocket. Because the chains are attached to the hidden sprocket, they will move with the hidden sprocket, snapping back at 15, and the visible sprocket will continue to rotate as the degrees continue to 16, 17, and so on. This creates the illusion that the chains are rotating around the visible sprockets. One more parameter that needs to be created is one we named sprocket initial. Its value is 90 degrees. We made this parameter so that our sprocket would not cross over into negative degrees, giving us faulty movement. Now we want to apply these calculated values to the angle constraint on the hidden sprocket. Right in the dialog box, at the bottom of the browser, the parameters can be assessed. We can select sprocket initial and note that it does not rotate the sprocket at all. Next, we want to add chain angle to sprocket initial in the dialog box and hit return for that equation to take. So the hidden sprocket should follow the drive sprocket. To identify which sprocket is the drive sprocket, we want to name it drive angle. That name will not affect the name and parameters. In the dialog box of drive angle, we can plug in degree numbers, so 1, 2, 3, and watch the chains move because of the movement of that hidden sprocket, until we get to 15, where the hidden sprocket snaps back, and because the other sprocket and chains are constrained to it, they will snap back too. Notice that the curved chain segment on the left never moved. There's a solution for that. First, the angle constraint with an offset of 7.5 degrees on the hidden sprocket needs to be suppressed so that a motion constraint can be created between the two hidden sprockets. There is only one angle constraint that should be driving the chain movement, and a motion constraint allows the other sprocket to follow the driving sprocket. To do this, we need to open up our hidden sprockets again. So let's turn the visibility off of our real sprockets. Open up the hidden sprocket assembly. select the hidden sprocket and turn its visibility back on. Close the assembly and save. When we come back to our tutorial file, you can see that the hidden sprockets are now visible. Now, we can add our one-to-one motion constraint between the two hidden sprockets, grabbing the inside region of the big circle in the center there. Once that is done, turn the visibility of the hidden sprockets off again, and the real sprockets back on. Test the movement by entering different values for the angle constraint on the first sprocket. The chain segment on the left is now moving with the other chain segments. We are turning off all our work planes so that our model is less distracting. In that last chain movement test, the chains on the hidden sprocket dipped down noticeably. We want to make that dip less extreme. To fix that, we need to add another parameter, which we call pitch angle half. We start it at 0 and go to 15. It will look much smoother if you go from -7.5 to +7.5. The vertical distance will be reduced quite a bit, and the transition from 14 to 15 will not have a big vertical component to it. From 7.5 to 8, the chain will not bounce up suddenly. It should just rise and fall as the sprockets move back and forth. So, we made pitch angle half, which is simply pitch angle divided by 2. And we subtract that from the equation already in chain angle UL. Instead of snapping back at 15, the chains will now snap back at 7.5. As you can see as we plug in degrees in Drive Angle's dialog blocks. That last chain movement test looked great, but there is one last flaw to fix. If we zoom in here, you can see that the sprocket's teeth are inside the pins of the chains instead of between them. What happened is that the visible sprocket is not in the same position as the hidden sprocket. We want to make another parameter we call drive angle shifted, which is unitless, and its equation is drive angle UL plus pitch angle half. For that to be incorporated into our modulus equation, we will change drive angle UL in chain angle UL's equation to drive angle shifted. So this shifted the sprocket teeth between the chain's pins, and everything is moving correctly. Now that the motion relationships are working properly, we can animate the chains in Inventor Studio. Go into Inventor Studio. The first thing you're going to want to do is set the view the way that you like it. We'll want to change from orthographic to perspective view. So now you can pan around, rotate your model to where you like it. Try to get a nice angle. When you like your view, you can go to Camera and set Camera from View, which will create a camera. It lets you do two things. It allows you to restore that view you liked after you've been working. It also allows you to select that camera for your animation. So now go into Render, and we're going to edit our scene styles. Now we like reflective ground planes to really highlight our model. So we're going to select the XZ reflective ground plane, and as you can see, it defaults to the origin of the model. So we're going to want to drop it down, -1.5, so that it looks like our model is above the floor instead of submerged into it. We're also going to turn off the shadows and save that. So now we're ready to animate. So open the animation timeline. Expand the front sprocket so that you can select the drive angle constraint. This is the constraint that you will be animating. Since the screws of the sprocket are 90 degrees apart, we only need to animate over a period of 2 seconds. To make this work, you'll have to set a constant speed, or else the chains will slow down every time they get to 90 degrees and then speed up past that. Let's render a single frame so that everything looks the way we want it to. We'll select camera 1, since that's the perspective that we're looking at. So now we'll change the aspect ratio to match the screen that you're going to show your animation on. And we like to select the pleasant lighting style. It's just nice to look at. For scene styles, you'll want to select the XZ reflective ground plane that you just edited. And now we're ready to render that single frame. And that looks pretty good. So if you liked everything you saw in that single frame rendering, the next step is to make a preview of your animation. Go to Output, and you'll want to animate over a period of 2 seconds. Select Preview, No Render, and a frame rate of 30. Then select Launch Player, and Render. And the name's fine. Set a resolution of 640 by 480. And that looks pretty good. So now the player's going to pop up. And let's put it on loop so that we can watch the sprockets go farther than 90 degrees. And as you can see, the motion continues all the way around. The final step is to fully render individual frames and stitch them together. We did this using Adobe Media Encoder. We set out to show you the most basic example of a chain traveling around 2 sprockets with the same amount of teeth. The chains on your mechanism are probably more complex than this, but it's a simple step to modify these methods for multiple chains traveling around sprockets of different sizes, with idlers, etc. For example, here's the drivetrain for one of our robots. If you have any questions or comments, please contact us through our website, and thank you for watching.